Okay, so today we are going to discuss now the index problem. So index problem for this Dirac operator. Okay, so you remember from Monday and the other days that we have this generalized Dirac operator. So this D was from C infinity of S to C infinity of S. And this was for any Clifford module bundle, right? So we have this. Now, it turns out that this is actually not any other operator. First of all, this is first order, right? So D was like some E alpha. You take a covariant derivative and then you Clifford multiply by these generators, by these frame fields. But basically, this means these are some matrices in local coordinates. And you differentiate the column and then multiply by matrices, you get a column again. So basically, this operator only differentiates once, right? So this is a first order. Okay, so this is important, we should not forget. This is first order differential operator, right? That's one thing one can easily see. Another important aspect of this operator is that this is actually is an elliptic operator. And is elliptic. So let me not define ellipticity right now, but let me just give you a kind of corollary of this condition for our D that's of immediate interest for us. So it follows that, I mean, this ellipticity implies that, so let me write it like this. If your manifold is compact without boundary, is closed, for example. So closed means compact without boundary. And that's the kind of situation that we are going to be in now. Without boundary. Right? So this ellipticity implies that this D has finite dimensional kernel and finite dimensional co-kernel. So this implies that dimension of kernel of D is less than infinity, and dimension of co-kernel of D is also less than infinity. And now this co-kernel, you just we notice co-kernel by definition is just like a linear algebra. You just take the target space, which is in this case the infinity of S again, but you divide it by image of D. I mean, this operator goes from here to there. I mean, for this concept, so you can go from V to W, for example, and co-kernel is this target space divided by image. That's the co-kernel. So it basically this number, cocardioid, measures how far D is from being surjective, right? That's what it measures, this number. And this number measures how far D is being injected. I mean, this kernel is 0 if and only if D is injected, right? So this is a measure of injectivity, and this is a measure of surjectivity. So basically, because this space is infinite dimensional, I mean, the domain and range of spaces are infinite dimensional. So basically means that this D is almost invertible. Modulo some finite dimensional corrections, D is 1 to 1 on 2. I mean, it's not, it's almost invertible. So, and then the idea now is the following. So we have a general concept called Fredholm operator, which is much more general than this. So definition. So imagine you have a linear operator between two vector spaces, say over R or C. Imagine you have a linear operator between these two vector spaces. This is called Fredholm. Exactly if these two conditions are satisfied. If dimension of kernel of T and dimension of co-kernel of T are both less than infinity. Now, I should give you a warning that usually Fredholm is discussed in more analytic, more kind of functional analytic situations. Usually, so let me put it like this, usually T goes from H1 to H2 from two Hilbert spaces and is bounded. And then we talk about Fredholm. We just say a bounded linear operator from Hilbert spaces is called Fredholm if dimensional kernel of T and dimensional co-kernel of T are less than infinite. But the concept is just very algebraic, I mean, in a sense, right? Because I just take it. And I need this more general, flexible context or definition because C infinity of S is only a pre-Hilbert space. It's not a Hilbert space. It's not complete in L2 norm, right? But nevertheless, the result, this theorem, this is a big theorem. I mean, shows that actually from here to there is already a Fredholm in this sense operator. And by the way, this D will never be a bounded linear operator from one Hilbert space to another Hilbert space. So that's some analytic technicality that I don't want to get into that. But I mean, this is good enough, this level of generality. Okay, so that's one thing. Now, so this is the idea of Fredholm. Now, what is the index? So if T is Fredholm, then we can define its index. Index of T is defined as dimension of the difference between these two quantities, right? Dimension of kernel of T minus dimension of co-kernel. So this is the fundamental concept of index. Of course, I mean, index can be defined only if the T is Fredholm. V and W need not be finite dimensional. In fact, in the finite dimensional case, this is a boring concept because it's independent of T. But what is really interesting is the case where these operators or these spaces are infinite dimensional, but nevertheless T is Fredholm. And this is the index thing. Okay, so before I go back to my general Dirac operator setting, let me just give you a little bit of description of the meaning of this. Maybe giving some simple exercises. Here is the exercise. If B and W are finite dimensional, compute index of T. And you will notice that it's actually independent of T. That's yeah. Okay, so but this, of course, dimension of kernel now it depends on T. I mean, if you have a matrix, its kernel can be anything from 0 to n dimensional, right? And dimension of co-kernel also can be definitely depends on T. But the difference is independent. So that's already shows that there is something magical about the difference. In fact, there are a lot of magical things about the difference. That's not shared by this and that individually, but the difference. And the most important thing is that this quantity is actually homotopy invariant. Okay, so this is the simple exercise. This quantity index is homotopy invariant. I mean, I won't prove it. I don't think I will use it. Yeah. I won't use it, but it's very important to know, and that's part of the importance of index. Because if you change the operator in a continuous way, in some sense, in some space of operators, the index won't change. This number won't change. That's a very important property. So this means that then this number is somehow susceptible to computation. If you have a number which is integer and does not change, if you change the parameters of your problem, then that's a wonderful number. It's a topological invariant, like winding number. So that's you can write down in some cases formulas for that, right? So that's and in fact that's exactly the situation. All right, so let me give you another exercise about this approach into infinite dimensional. Exercise 2 today. So define T from L2 of n. Okay. N I never consider 0 as a natural number, so it's from 1 to infinity to L2 of n. So this is defined like this: T of say A1, A2, a sequence of numbers which is little L2. It's just pushing backward. It's A2, A1, this. And the idea is that you want to compute, you will show that T is Fredholm and compute its index. So T is Fredholm and compute index of T. Okay. So that's, I mean, so you can say a lot about this, the idea of index and Fredholm operators in very abstract setting without any geometry and topology, just working with these concepts. But that's not what we want to do. We want to go back to our problem and then clearly formulate the index problem for this. Okay. So then let me write down the index problem for the operators. Oh, by the way, one remark I should make here is that dimension of co-kernel, you can replace it actually by dimension of kernel of T star. So you can write actually, I mean, it's also is equal to dimension of kernel of T minus dimension of kernel of T star, right? So, I mean, I'm assuming we are in a situation where we can talk about T star. For example, you are in a Hilbert space or pre-Hilbert space situation, and you construct this T star that satisfies a usual property. It's a bit of delicate notion, actually, but let's, and then this dimension of co-kernel, you can replace it by dimension of kernel of T. T star, sorry. So this is. So check this formula. So this is another exercise. Check this. That's a linear algebra thing. It's good to check this. Okay. So now we have our concept there. So now the index problem is this. Index problem for Dirac operator. So the question is, compute this index in terms of some topological data. Compute index of D in terms of topology M. I mean, it's a topological invariant. So if you change, for example, Riemannian metric, this doesn't change. So it means that this should be something expressible in terms purely in terms of topology of M. And that's the problem. And that's what Atiyah-Singer index theorem actually solves. Before I write down the solution, let me now see what I need to say here. Okay, now, okay, so what is the answer to this question, by the way? Do you know the answer?
Is it the Euler characteristic?
Is it the Euler characteristic? That's a good guess. No, it's not. Are there any other guesses? The problem is actually the way I formulated this is 0. So the answer is equal to. So this is, I should call it, this is index non-problem. This is not a problem. Well, I mean, the solution of this non-problem is the index of D is equal to 0. What's the reason for that? Didn't we prove that D is self-adjoint? We checked that D is self-adjoint. I mean,
It doesn't have a boundary.
What's that?
It doesn't have a boundary. It's a closed manifold.
M is a closed manifold, right? No boundaries. So yeah, exactly. So index of D is equal to 0 since D is self-adjoint. I mean, it's here. So this is equal to 0 if T is equal to T star, right? T is equal to T star. So now, since D is equal to D star, as we checked. So for D per se, there is no problem. Now, let us check this in one case that we know how to handle concretely and on kind of with our own hands. And that's actually related to comments that Jeremy made about Euler characteristic, which is relevant here. So let's look at the example of, let's look at one example of that we can actually know what this D is. And that example, by the way, is just remember case of, remember this bundle S was equal to the bundle of exterior algebra of cotangent bundle, right? So this is direct sum of wedge K of T star of M, right? K from 0 up to whatever. Okay, so that's that case. Now, C infinity of S in this case is equal to direct sum K from 0 up to and C infinity of these things individually in a space of sections. But then we just gave, because this is a just long notation, we just gave a special name to this. This is equal to, these are differential forms, right? Differential forms are smooth sections of this bundle. So this is equal to, and then we have notation omega K of them. So D in this case goes from these differential forms, right? Okay, so let's call this omega of M. Now I don't put any index. It means that I'm taking the direct sum of these things, right? Just to lighten the notation a little bit. So this goes from omega of M to omega of M. Sometimes people put a bullet here also. So maybe it is, most of the time people put a bullet there. It means that I know that this is a direct sum object. So we just put it. It's a standard notation. Okay, so this D goes from direct sums of all differential forms to direct sums of all differential forms, in this case, for this, generalized Dirac operator. And actually, I said that this D, in fact, is just D plus T star. Although we didn't prove it, but okay, so let's, D is equal to D plus T star. But D, of course, is Theorem. Remember, D goes from omega K and to omega K plus 1M. This is D, here I put it like that, and then D star goes in the other direction. It lowers the degree, right? D star lowers the degree. Okay? And of course, it's okay here to have these operators that change degree. So one of them raises the degree, the other one is lowers the degree, but the two together work together and then gives us. So this is a generalized Dirac operator. So D plus T star is a generalized Dirac operator. And now let's compute the index. So we are supposed to get 0. But imagine we didn't know this general fact, which is much more general than this case, and we wanted to compute the index in this case, see what we get. Okay, so let's go on and compute. What is the index of this operator? Actually, it's a kind of good exercise to compute the index in this case. And find that this is 0. So let's compute the index. So this is my D now, the Dirac operator in this case. What is the index of D in this case? Is equal to what? Well, what is kernel of this case? Kernel of D. Let's compute. Well, this is just the set of all 0 form, 1 form, up to n forms, such that d plus d star of this is 0, right? D star of, I mean, acts kind of collectively, omega 0, omega 1, omega n is equal to 0. Okay. So what is that? That just, let's, I mean, this is equal to, I mean, well, there is this star of omega 1 which turns into degree 0. So I have to put it here. This star of omega 1 is here. And then we have got, for degree 1 things, I've got d of omega 0, okay, plus this star of omega 2. They contribute to degree 1 term here, right? Because there is something here, this one, and so on.
Sorry, why would the first term be d star of omega 1? Would it? I would have thought it'd be d of omega 1.
D of omega 1 is going to be something of degree 2, right? I won't put it here. This I reserve it for degree 0 terms. This I reserve for the degree 1 term. I mean, these are like slots here, right? Like that. Right?
Oh, right. Yeah, sorry. I got mixed up.
Yeah. I mean, there is a little bit of, I mean, things here. So we have to, I mean, it's just an organizational matter. It's nothing deep, but we have to be a bit organized here. So that's it. Okay? I mean, there is no other contribution. D of omega 0 is degree 1. So, but d star, of course, d star of omega 0 is 0. So that doesn't contribute. But d star of omega 1 contributes something here, right? So that's okay. So, and then you go on. Now let's look at these equations. I mean, this is 0. The vector is 0 if all components are 0. This is 0. And then we have got d of omega 0 plus d star of omega 2 has to be 0, right? And we just, what's, by the way, what's the next term? Well, what's the next term in this case? So I've got here for this, I get d of omega 1 plus d star of omega 3. So let's write the d of omega 1 plus, I mean, I'm going to write it in a more symmetric form. So I just write it here. This is 0 plus d star of omega 1 equal to 0. Yeah, and then there is d of omega 1 plus d star of omega 3 equal to 0. Here is d of omega 2 plus d star of omega 4 equal to 0 and so on. Okay. Right. So now I want you to show from this, you conclude from this that actually the following thing. So here is another, okay, so this is very easy, but I just give it as an exercise 4. From here, I want you to conclude that delta of omega 0 equal to 0, delta of omega 1 equal to 0, delta of omega 2 equal to 0, so on. But delta is really the Laplacian, which is d star plus d star, this star d. I mean, alternatively, this just means that d of omega 0 equal to 0 equal to d star of omega 0. D of omega 1 equal to 0, which is equal to d star of omega 1. Well, the star of omega 1, we already have it here, that's 0. So all you have to do, you have to show that d of omega 1 is equal to 0. So, and then d of omega 2 equal to 0 equal to d star of omega 2. So either, I mean, this is if and only if, because delta is d star. You see from here, you can prove that this is, I mean, we did it in class already. This is equivalent to that. So then what does it mean? These equations means that omega 0, omega 1, omega 2 are harmonic forms, i.e. omega 0, omega 1, omega n are harmonic forms. Harmonic differential form. And I told you there is a big result in well, I mean, global analysis or differential geometry that tells you that dimension of the space of harmonic forms is actually dimension of cohomology. So this is called Hodge decomposition theorem or Hodge theorem. I mentioned this several times and I used it maybe day one even. So Hodge theorem says that dimension of kernel of delta Q. Now delta Q means, of course here you can just say delta 0, delta 1, delta 2, but it's not. It's kind of ugly to use this notation. But dimension of kernel is equal to dimension of the Ram homology group, right? Q, the Ram of that. Which is, there is a notation for this. This is called the Q Betty number, right? Beta Q. This is Q Betty number. Okay, either this definition or other definitions of Betty numbers, they're all the same, and this is dimension of kernel. Okay, so what did we discover? We discovered that dimension of kernel of T is actually sums of Betty numbers. Okay, so here follows that dimension of kernel of D plus D star as an operator that goes from full sums of differential forms to full sum again is equal to beta 0 plus beta 1 plus beta. It's sums of Betty numbers because this you have as many freedoms as dimension of delta 0. This you have as many freedom as dimension of kernel of Laplacian 1 and so on. And these are sums of Betty numbers. Okay, so now what is the dimension of co-kernel of this? Well, as I said, you can just work with kernel. This is equal to dimension of kernel of the adjoint of this, but the adjoint of this operator is really like this star plus D again. This adjoint operation has this property. So again, this is equal to beta 0 plus beta 1 plus beta. So when you subtract the two, so you get index equal to 0. I mean, as I said, I did this calculation in order to, because I need this example more and more. So this is the first thing that, so if you don't touch anything, you just take the Dirac operator that's given to you by nature, which is like one of the examples that, I mean, generalized Dirac operators that's given to you, like this. If you don't care and brutally want to compute its index, it's 0. And that's not a very interesting problem because we know the answer is 0, so it's just 0. So, but there is, but we know that there is an interesting invariant that we could compute here, and that was Euler characteristic, right? So the Euler characteristic, let's see, how did we reach? How did we compute Euler characteristic in terms of this? Well, we kind of split this thing, omega, into two pieces. And we kept one half for the domain space and gave the other half to the target space. So this is but index of d plus d star. Now the splitting here is very simple. It's from direct sum of omega 2I, okay, of m, to direct sum of omega 2I plus 1 of m. This is not a trivial number. This is a very interesting number. This is, well, you go through the same calculation and then you get that this is equal to beta 0 plus beta 2 plus beta 4, so on. That's equal to beta 0 plus beta 2 plus beta 4. And then you subtract beta 1, beta 3, so on. Right? So this is nothing but sum minus 1 to the I, beta I over I. And of course, this is well-known Euler characteristic of that. So Euler characteristic can be obtained as index of an operator, as index not of the full Dirac operator, but half of Dirac operator. And that's a very general phenomenon we want to discuss. So in order to make this index problem more interesting, we have to split space of spinors into two pieces and take one piece for the domain, another piece for the target space, and then that would be our index problem. So I'll just write it down now. I talked too much, I think, without pausing. Sorry. Do you have any questions? Okay, so now.
Hi. Hi. Can we just say that d plus d star is self-adjoint?
D plus D star. Ah, yes. Okay, now D plus D star, this one is not self-adjoint. I mean, yeah, it looks like a paradox because you could say, hey, how come? I can just say D plus D star is D plus D star. But remember, D plus D star, this one, it goes from even forms to odd forms. For self-adjointness, you need to go to same space. Because, you know, I mean, if you go, so imagine, I mean, this is again pure linear algebra issue. If you have a kind of operator or matrix in linear map, T from V to W, I mean, anyone who just writes a linear map from V to W, he or she deprives herself or himself of the right to say that T is self-adjoint. Because, I mean, what does self-adjoint mean? T equal to T star. This means that they should go from same space to same space. But remember, T star goes from W, I mean, if these are Hilbert spaces, to V. No? So we don't even have a right to say that this T is self-adjoint because it's going from a different space. And certainly in this case, it's not true that such things. I mean, you get a different, you get a map from a different space completely into your domain again. This was a good question. So are you okay now with the answer?
Yeah.
Yeah, I mean, okay, so this was a good observation. I mean, here, it looks like that I use that cheap argument that I used here, I could use it here, but no, this is a more subtle situation. All right, now.
So in this second case where you switched the domains and got that the index is the Euler characteristic, is this isn't, do we still regard this as a Dirac operator? Because now the domains are different, right?
Yes, I'm going, indeed, I'm going to discuss this. So this is like Dirac operator on kind of right-moving spinors and left-moving spinors, kind of. That's the decomposition we are going to introduce, yes.
Okay.
So yeah, I mean, now you understand those right-moving, left-moving kind of spinors better in this context. And you know that we have to go into that situation. Yeah, I mean, this also, this is usually denoted by D plus. I will introduce the notation. That would be the notation D plus. So that's what I want to introduce now. Yeah, that's right. So that's, yeah, formally, it's not our original. It's really half of the Dirac that matters in this case, at least in an even dimensional case. So now let's we want to consider, we want to focus on the case where dimension of M is even. So from now on, so there is an assumption, dimension of M is equal to N is equal to 2M. This is an even number, so this is very important now. And you will notice why we don't have a kind of interesting index problem for differential operators on closed manifolds, even odd-dimensional closed manifolds. You will see that soon. But let me just. So now we have to go back to drawing board, so to speak, and look at Clifford algebras. Recall. Clifford algebra. We have this CL. I mean 2M, right? So this was like CL of any V with positive definite inner product, and we tensored it with C, right? Well, dimension of V is equal to 2M, sorry. Okay, anyhow, either in this coordinating or in this abstract coordinate-free version, we have this algebra. Its dimension is 2 to the 2n, and we know that this is just matrix algebra. I mean, this is isomorphic to end of endomorphisms of just space of the spinors. Its dimension, of course, is n, 2 to the n. Okay. So dimension of delta 2 to the n. Complex spinors. Okay, now there is an element here which is very important. That element is called volume element. I believe this is also chirality element. Because it defines the handedness, really. This is chirality element. It's defined like this. It's really just this omega is the following element, is I to the power, I believe m. I to the power m, E1, E2, En, right? Yeah, I think that's it. Okay, so this is an element. So this is for any oriented, I mean, we are assuming this is basically, I mean, this V has an orientation for any oriented orthonormal basis of V. Okay, this I to the n, of course, is just a convenient factor that's not play a big role. But we define an element, and now I'm saying for any, so you better check that this element is independent of choice of oriented orthonormal basis. So this is an exercise. I mean, this is a pure linear algebra exercise, a good exercise. Maybe I've given it before, but let's see, check that omega is actually, it's a God-given element. It's independent of choice of orthonormal basis. Check that omega is independent of choice of yeah. You need both conditions. It should be orthonormal and it should be oriented, I believe. So that's okay. Now, what is the property of this element? This element in the has the property that omega squared is equal to 1. Moreover, it also anti-commutes with elements of the Clifford algebra, and so let me write it. Another Clifford algebra. So lemma is that for any V, not in the Clifford algebra, just in this small part, which is just the generators, basically, right? V is the generators of this algebra. For any V, little v, cap V, we have that V times omega equal to minus omega times V. Yeah, we are in the even case, right? So we have that this omega, so x times omega equal to omega times x for all x belonging to the even part of the Clifford algebra. Okay. Oh, this 2n is wrong. I'm sorry. It should be 2n. I don't want to change notation all the time. This is 2n. And x times omega equal to minus omega times x for all x belonging to odd part of the Clifford algebra. So, I mean, if you prove this, you just immediately see that, right? Because this is just, yeah, because even part consists of products of even number of vectors, odd part consists of products of odd number of vectors. Except that that odd number is not fixed. It could be 3 times plus 5 times of vectors plus 7 vectors multiplied together and so on. Okay, so that's so this is very easy. So I mean, just leave it to you to check. Okay, now this exercise implies that you have this element over any actually like I mean over any oriented Riemannian manifold, right? So that there's a field of elements inside Clifford algebra which is given. So basically what we want to do, we want to globalize this. Globalize omega. So it means that for any oriented Riemannian manifold, there is this section, which is a very important section, that exists omega, a smooth section of the Clifford bundle. I mean, complexified Clifford bundle. So I just put it like this. It's convenient that Clifford's name starts with C. So I just complexify this. So this is an interesting English last name. Okay, so Clifford. Section of the Clifford bundle. Still denoted by omega. But remember now this omega, of course, changes from point to point and lives in this strange space, Cliff Tm, right? X. Okay. So there is this object that changes from point to point and it defines this kind of field for you inside this. And that's very useful because now you can just define this, define it globally. Okay, now, if I have a module over this, I can decompose the module using this element. Okay, right? So for any Clifford module, I should more precisely say Clifford module bundle, S over M, we can decompose it now into two pieces. So get this decomposition S equal to S plus, direct sum, S minus. How does this decomposition work? Well, we have this element omega, right? This sort of chirality or volume element omega. So we can just
what does it mean by saying oriented orthonormal basis of a vector space?
Sorry?
What is the oriented basis of a vector space? What is the oriented?
What is so? Yeah, so there is a concept in linear algebra. There is a concept of orientation for real vector spaces.
Okay.
So so this is not emphasized in linear algebra texts, unfortunately. So this is orientation for a. I mean, it's defined only for real vector spaces. It's not defined for complex per se or vector spaces over other fields for real or a real vector space. Okay, so let's say finite dimensional. I mean, there are about, I don't know, 3, 4, 5 different definitions. Here is, I tell you one of the definitions. It's a choice of a ordered basis, So it's a choice of an ordered basis. I mean, you don't need any inner product for that. This is just ordered basis. I just put F1, F2, Fn. It means it appears in a given order, and this is a basis. It's a choice of an ordered basis for V, but up to an equivalence relation, right? Up to an equivalence relation. So what is that equivalence relation? The equivalence relation is this. We say we declare a basis, an ordered basis. I don't know what is basis for you, but basis doesn't have a natural order. Although we just write like E1, E2, En, but this is artificial. I mean, there is no natural order in a basis. But if you want to emphasize the order, you have to say ordered basis. That's anyhow. So F1, F2, Fn is equivalent to, say, maybe I just write E1, E2, En. Again, another ordered basis. If the determinant of A is positive, and A is the matrix that carries F1 to, is defined by this equation A of Fi. equal to B. We know that this determinant is not 0 because it sends basis to basis. And if the determinant of this matrix or this operator from B to B is positive, I mean, to define the determinant of a map, you don't need a matrix. You just need a map from one vector space to itself. Again, it's like to itself. Then you have a determinant, right? So then once you take the determinant is positive, you say, so exercise, take that this is an equivalence relation. And also check that there are only 2 equivalence classes. Of course, it has to do with positive and negative number. And check there exists just 2 equivalence classes. And each equivalence class is called an orientation for your space. Okay?
For trivial vector spaces, there's only one, right?
Just a second, let me finish my, I will get back to you because that's a kind of check this, and there exist just 2 equivalence classes, and each class is called an orientation. An orientation for V. Okay? And I tell you this, a vector space, I mean a real vector space, doesn't have a natural orientation. You cannot guarantee that you choose an order. I cannot hear you. Someone is talking, but I can't hear. Okay, so there is no natural orientation for a vector space, and that's the reason that manifolds can be non-orientable. That's the essential reason, because there is no canonical section again. That's the question of section. I made a comment yesterday that's also relevant to that issue. There's no natural choice in this case. There was a question someone asked about trivial vector space or something. What was the question?
Yeah, so there are only one equivalence class for 0.
Oh, you mean for zero-dimensional vector space, right?
Yeah.
That's,
There's no basis in that case, though.
but there's a basis. No.
For a 0-dimensional vector space.
No, if there's no basis, then I will get into an existential crisis.
I mean, it's just the 0
it's
element.
the empty basis. No, it's the empty basis.
Oh, okay, sure.
Yeah, absolutely. Yeah. It's empty set. Yes, that's the basis. Empty set. And now can we define even an orientation for zero-dimensional vector space? Because there is no map. So, okay, so for zero-dimensional vector space, it seems zero-dimensional vector space has no orientation.
I mean, you can't put an order on your basis if it's the empty set, right?
What is the order?
That's my point. I don't think you can put one on the empty set, which is your basis, right? So you can't really define orientation, right?
No, so wouldn't that be an empty order? And you'll only have one orientation then?
I didn't.
Oh, right. Okay.
Huh? I didn't hear what you said.
So you can have an order on the empty set, right? It will just be the empty order, I guess. Now it depends if you want your ordered sets to be empty or not.
So what is the order? What is order on a set?
So it's just a relation, right? And sure, the relation on an empty set is just going to be the empty relation. So it will be a map from the empty set times the empty set to the empty set. And there's just one map.
Okay, so there is, but there is no map, right? Because if you want to define a map, you have to, well, map maybe is. So what should we say? Should we say that there is no orientation, or there is a unique orientation? Which one is your choice?
I would like to say there's a unique orientation.
There's a unique orientation. Huh?
Yeah.
I like to say there's no orientation to make it even more mysterious. I mean, so just zero vector space.
Well, I think there's two ways to orientate a zero-dimensional vector space, but there's only one type of orientation for a basis. So it's either positive or negative, whereas in regular vector spaces, you have positive and negative orientations for bases, whichever way you orientate them.
So let me stop the thing because because this is.
Oh, it seems you weren't recording.